Good afternoon, students.
Good afternoon, sir.
So I have not yet received your second internal marks, so could not find about the performance of you people in your second internals. But anyway, once we can receive the second internal marks, I will be uploading all those in the user. So for the time being, we are looking at the concept of support vector machines. We had a basic concept of support vector machine. We saw the different mathematical aspects and concepts of support vector machine too. And in this class, we will be seeing some more details. Right? A normal support vector machine is applicable for all varieties of applications. But sometimes when the nature of your data varies, we need to make some changes in support vector machine so that it is suitable for all the applications. So we will see some different variations of support vector machine in this class. Let me share my screen. Is my screen visible?
Yes, sir.
Non-linear SVM, right? That is what we are going to see today. And if I say non-linear SVM, then you can clearly understand that we also have another concept called as linear SVM. The majority of the concepts which we saw earlier fall under the category of linear SVM. So first you must know what is meant by linear and non-linear. It doesn't have any specific role to play with the SVM, but this linearity and non-linearity rest with the data, with your specific data. So if your data is linear, I am going to call it as linear SVM. If your data is non-linear, I am going to make some small changes and then I'm going to call it as non-linear. So SVM is usually a linear classifier which learns n-1 dimensional classifier for classification of data into two classes. That means when you have two features, right? When you have two features, number of classes also will be two. Right? You say, for example, a circle and a star mark. Then the number of classes also will be two. But how do you classify this data? With a single line. That's what we saw earlier. Right? So if the number of features is n, your dimension hyperplane will be n-1. This is an example for the linear data. Right? A linear data with the number of features as 2. So number of classes also as 2. So your hyperplane will be n-1 dimension. So 2 minus 1 is a single dimensional hyperplane or a classifier line, which is nothing but a line. Right? So here we are not bothered about the dimensions of the line, but I am bothered about the data. So when I look at my data, clearly all the blue color circles are on one side and all the red color boxes are on the other side. So our normal SVM will do. You can make use of the SVM which we have learned so far. Try to make a try to choose a hyperplane which will have a maximum margin between the closest possible blue color circle and your red color box. That should do. But sometimes, or I should say, most of the time, you will face some applications where you will face data like this, right? And this type of data come under the category of non-linearity. Why do I say non-linear? It is completely mixed. The yellow color dots and the purple color dots are completely mixed, and I am unable to separate this with a single line or a single plane or whatever it may be. Right? So these type of data are non-linear, and practically most of our data are going to be non-linear in nature. Right? But still, as I told you, our SVM is applicable for all sort of applications. So I should be confident enough to use SVM also for this type of data to get good result. Right? And literature survey or the research says that SVM can be used for classifying a non-linear data set also. In that case, my SVM is going to be called as non-linear SVM. So how can I do? Is there any change in the SVM process? Is the maximum margin going to change? No, right? What we are going to do initially as a pre-processing step is I am going to convert this diagram, which is on my right hand side, to a version, a different pattern in such a way yellow color fall under one category and purple color fall under one category. How I'm going to do that? This can be done by projecting the data set onto a higher dimension, right? The diagram which we have is going to be only a two-dimensional one, right? It has only two features. Now I'm going to project it to a higher dimensional one, maybe to a 3D structure. So when I view the same diagram, which I have on my right-hand side in a 3D way, in a three-dimensional way, then I can see that yellow color and purple color are not actually mixed. Because I am viewing it in the 2D form, it appears to me as a mixed data. But when I look it in the 3D version, it is not so. So my data should be converted into a 3-dimension. So for that, what should I do? I should include one more feature. Now this axis is x1, x2. But only when I go for a 3D feature, say for example, x1, x2, and x3, I can get a better representation of my data. Right? So this is what we are going to see now, how we can translate or convert our 2D representation of a nonlinear data into a higher dimensional. The data set is clearly a nonlinear data set, and it consists of two features, say x and y. If somebody's mic in the on condition, can you please mute it? Okay, thank you. The data set is clearly a nonlinear data set, and it consists of two features, say x and y. In order to use SVM for classifying this data, my nonlinear data, I am going to introduce another feature, z. Right? When I include this another feature z, the same yellow color circles and purple color circles will be represented in a 3-dimensional space. That means I will have x-axis, I will have y-axis, and also I will have z-axis. So actually, by including one more feature, I am increasing the dimension, and I'm going to say, yeah, I'm going to convert it from 2D to 3D. This is what happens when I view the same data in a 3-dimensional way. Here I have x-axis, here I have y-axis, and also I have z-axis. Right? So when you view now, you can clearly understand that purple and yellow color are not mixed. Right? But in the previous data, it looked as if both are mixed. Right? Or I can say that you are actually viewing the same data from a top view. When you look at from a top view, it will look like as if both are mixed. One is within another. Yellow color radius. The radius is the third axis. Right? Radius is the third axis. The yellow color is within your purple. So the radius of yellow color is small, and the purple of radius of purple color is a bit more. So when you look at it in a 3D form, when you include radius also as one of the feature, you can see that they are not mixed. Now this 3D data, this nonlinear data is converted into a form which is a linear form. When I say linear form, not exactly linear, which I am able to classify into two classes. Right. The first dimension representing feature x, second representing y, and third representing z. In this application, my z is nothing but the radius of the circle. So this radius of the circle is the one which can differentiate my purple color and my yellow color. Right? So yellow color radius is small, purple color radius is large. Now, clearly for the data shown above, the yellow data points belong to a circle of smaller radius and purple a circle of larger radius. Thus, the data becomes linearly separable. So, if you use SVM, and in addition to SVM, if you have a pre-processing step to convert your two-dimensional data into a three-dimensional data, then you can say that is called as a nonlinear SVM. The real idea is you are not going to make any changes with SVM. All the concepts which we studied, the mathematical equations, the derivations remain the same. We are doing some process with the data additionally to convert it into a not a linear fashion. Now, how can I go for classifying these two? Not with a single line. Not with a single line. Only when the dimension is 2, 2 minus 1, I can go for a line. But now the dimension is 3, 3D. Right? So when I go for a hyperplane, it should have a 3 minus 1, 2D. So 2D is nothing but a plane, right? Or a square, or a rectangle, or anything of that sort. A 2D structure can be used to classify. So this is the basic concept of nonlinear SVM. So my question is, in SVM, how can we include this process of converting a 2D into? So in machine learning, a trick known as kernel trick, right? You would have, if you have referred any blogs or any website about machine learning, you will normally come under this word called as kernel. Right? This kernel is a mathematical equation which is used to convert a linear a non-linear process into a linear process. Or otherwise, I can say this kernel is a mathematical equation which helps the SVM to classify a non-linear data set also. Right? Kernel, nothing but a mathematical equation. Kernel transforms the linearly inseparable data into a linearly separable one by projecting it into a high dimension. Whatever we have seen so far, the same thing will be done by a kernel. A kernel function, we call it as a function because it is something like a Gaussian function or something like a mathematical equation, is applied on each data instance to map the original nonlinear data points into some high dimensional space. So it will be like f of x. X corresponds to each data point. So when I apply that, when I use that x, or when I substitute that original data for x, I will get f of x or something different where I am going to have a higher dimensional space. These mathematical equations, these transformations are called as kernels. Right? Popular kernels which we use with SVM are polynomial kernel, Gaussian kernel, RBF kernel, Laplace RBF kernel, sigmoidal kernel, ANOVA kernel. It's not ANOV, it is ANOVA, ANOVA, ANOVA RBF kernel. So these are mathematical equations which are used for this conversion process. So when I say kernel SVM, you will immediately get that my data which I'm going to use is a nonlinear data. If you feel that your data is nonlinear, kernels are not at all required. You can straight away go with your normal SVM. These are some of the different kernel functions which are available for usage by the machine learning engineers. If you have time, you can go through these kernels. Some of the expressions I'm going to give you: polynomial kernel, it is popular in image processing. So when I give these two data points, xi and xj, it is going to give me an output which is in a 3D way. Not exactly 3D, a higher dimensional data. Gaussian kernel, again you can see that k of x comma y, it will need two inputs. Right? So two inputs, x and y, are non-separable. So when I go for these type of representation, I can get a data point. When I plot that, it will be linearly separable one. Gaussian radial basis function, again you will have a formula. A normal, we do not know whether this is a kernel or not. If you look at Gaussian function, I am very sure you must have learned about this Gaussian function. But this function, how can we make use of in our SVM to convert a linear data, sorry, a non-linear into a linearly separable one? That is what is interesting. And then you have Laplacian RBF kernel, k of x comma y, hyperbolic tangent kernel, another formula we have. All these are mathematics. This is where mathematics play a major role in the machine learning. Right? I don't think machine learning is some fantasy world like how we fly in the sky or move in a different way. It's not like that. It is all those engineering concepts which we have acquired so far. Into practice, we get some different called as machine learning. Sigmoidal kernel, ANOVA radial basis kernel, and so many kernels are available. Okay? So just try to have some idea on that, and I plan to give the first assignment on this specific topic. If it is okay for you, we can, we can proceed with that. How a kernel is used in the input side of a support vector machine, and how a data is converted to a higher dimension space. You can browse, you can take any application also, and then I want you to write or understand or project in your own words how a data, a non-separable data, when applied to, maybe we can take a simple Gaussian function which you are comfortable with, right? When I apply this, how the structure of the data differs. Maybe you can take it for an image, you can take it for a text, you can take it for a signal, and then tell me how SVM is able to convert that. I want to have some practical application for conversion of this 2D into a 3D form. Can we have that as a first assignment? Yes or no? Right? You have a data. You take any image or any text or any signal data, right? And just assume when you apply Gaussian function to that, right? How that data, pictorial representation of the data, how it is changed to some other form, as I gave a hint in the PPTs. Then how SVM is used for classification. If you refer any kernel-based SVM in the Google, I think you will get an idea. And maybe I am interested to give this as an assignment for you. But are you comfortable with that? That's what I want to know. Say yes or no. If that is the case, I will give time till the end of your working day, and then you can submit your assignment. Is it okay? Yes or no? I need some
Yes,
answer.
sir.
Yes, Angel?
Yes, sir.
Yes. So please go through that. I can give some assignments like applications of machine learning also, right? But that will not be useful for you. Right? Maybe this time when I say this assignment, it looks a bit difficult for you how I'm going to do that. But please explore, right? When you explore things, definitely at the end of submitting your assignment, you will get some more information on how we can go with that. Right? Otherwise, writing again an assignment for medical image processing and all those stuffs will not be used. If you can write, if you refer Google, I'm sure with Python or MATLAB, some codes also will be available. You take that. I'm not asking you to write new code. You take that, go for your Python or MATLAB page, try to run that and try to take some output and visualize how your data is changed just by the help of a Gaussian function. We would have studied Gaussian function more time, but we would not have realized the real usage of an Gaussian function or any. You take any function. If it is in the Google, if some other function is given, no problem. I just want you people to understand a bit more how this non-linear data is going to be separable into a linear data, because this is not only common for SVM, it is common for most of the machine learning. So I think the assignment will be useful to you also. If you feel any difficulty or anything, if you are not able to proceed with that, maybe I can change this at a later time, right? So I want you people to submit within maybe 1 month. We can have, I think we'll have another 1 month. This is March, today is March 18th. March 18th. By April 18th, I want you people to submit your assignment. We just go to Google, just browse and collect the information. That is what I'm asking from you, right? Some Python code is there. If there is anything, try to execute that, get the result and check how the data is. Because that point is hidden in most of the blocks. People, when writing the blocks, they say that it is converted to 3D, then given to SVM, it classifies. But I want to check how actually things work. So definitely it will be of interesting to you people. So the last date is April 18th. April 18th, you need to submit your assignment. This is the only assignment, no other assignment. So it will carry 10 marks. 10 marks for your assignment. Right? I will just go through how you have understood the concepts of conversion. I will also put that assignment question in your Google Classroom, because I am not sure how many of you would have understood the question itself. Right? I will put that question in the Google Classroom, so you can later look at that and try to start doing your assignment. Let me mark the attendance. Amulya,
Yes, sir.
Judson, not there.
Present, sir.
Samir, Judson
Justin
present.
will. Yes, sir.
I think Judson is switching on your. You are entering the EduServe and you are leaving somewhere. And suddenly, whenever I take attendance, you are coming back. Am I right, Judson?
No, sir. Network issue, sir.
Really honest?
Yes, sir.
Okay, thank you. Samyukta,
Chat box, sir.
okay. Angel,
Present, sir.
Ajit Pawan,
Prem, sir.
Abhinaya,
Yes, sir.
Kiran Kumar,
Yes, sir.
Manideep.
Chat box.
Okay. Banu Teja,
Yes, sir.
Jennifer,
Yes, sir.
Priyadarshini,
Yes, sir.
Jeevan,
Yes, sir.
Afreed,
Present, sir.
Jayant, chat box. Okay. Vikas,
Present, sir.
Paul Finney,
Present, sir.
Bhuvaneshwar, absent. Sumant Kumar, Ramesh Kumar,
Present, sir.
Neeraj Kumar,
Yes, sir.
Zubair,
Present, sir.
Kirti,
Yes, sir.
Kirti,
Yes, sir.
Kirti absent,
Sir, present, sir.
Kirti present. Dinesh,
Yes, sir.
Tejaswan,
Yes, sir.
Chandana Priya, absent. Karthik,
Yes, sir.
Vijay Kumar,
Yes, sir.
Soman,
Yes, sir.
Anish,
Present, sir.
Rex Vimal,
Yes, sir.
Harshavardhan,
Present, sir.
Uday,
Yes, sir.
Sakib,
Present, sir.
Siddharth,
Yes, sir.
Praneeth,
Yes, sir.
Salome,
Yes, sir.
Libinson,
Yes, sir.
Libinson is
Yes,
there.
sir. Oh, yes, sir.
Alan,
Yes, sir.
Alan
sir.
Joshua.
Yes, sir.
Okay. Ronan,
Chat box, sir.
okay. Sai Kiran,
Yes, sir.
Joshiba,
Yes, sir.
Shiny, Shiny, not there. Shiny absent. Jasmine.
Yes, sir.
Kavya.
Yes, sir.
Jayasurya. Jayasurya. Absent. Jona Paul.
Yes, sir.
Manasa. Manasa absent. Ashrita.
Present, sir.
Narasimha Reddy.
Yes, sir.
Puneet Kumar.
Yes, sir.
Shiny Rebecca. Shiny Rebecca. Okay. Joshua.
Yes, sir.
Nagakiran.
Yes, sir.
Suraj.
Yes, sir.
Monica. Monica. Okay. Taufik.
Yes, sir.
Manideep.
Present, sir.
Dikshit.
Present, sir.
Maria Angel.
Yes, sir.
Amrut.
Yes, sir.
Pavan Kalyan.
Yes, sir.
Okay. Sainath. Gautam. Gautam. Gautam absent. Jagat Chandra. Vivekananda.
Yes, sir.
Shashank.
Yes, sir.
Sai Ganesh.
Yes, sir.
Gopichand.
Present, sir.
Ritvik. Ritvik. Ritvik absent. Solomon. Solomon Raj absent. Sudarshan.
Yes, sir. Present, sir.
Sujit.
Yes, sir.
Suresh Kumar.
Yes, sir.
Sunny.
Present, sir.
Amrita Das.
Present, sir.
Absentees number 24. Bhuvaneshwar. Number 24 absent.
Sir, he texted in chat, sir. Bhuvaneshwar.
He has typed in chat.
Yeah, yes, sir.
Okay, pal, thanks. Then number 36. Chandana Priya. Absent. 63. Gautam. 67. Gautam present. 63 is Shiny John. I will read out the register numbers 36, 63, 67,
Yes, sir. 67.
67 percent.
Present, sir. Present.
71, 122, 132,
Sir, 132, sir.
132 percent.
Yes, sir. 132.
122 also.
122 also present.
Yes, sir.
And 133. I'll read out the names, numbers again. Number 36, number 63, number 71, number 133. So if you don't have any queries, you can leave the Google Meet. If you have any queries, you can stay back and get your doubts cleared from me.
Hello, sir. Sir,
Yes, Suresh.
sir, have
Yes.
machine learning.
I could not hear you.
Sir, sir, I have ideas, sir. One idea, sir.
Okay.
Like in nowadays, in
Your voice is breaking, Pa.
railway track system for detection.
Can you
Sir, in
can you
railway track,
just
sir, can you hear me? Hello,
send
sir.
me a mail? Can you just
Okay,
send me
sir.
a mail? Huh? Your voice is
Okay,
breaking.
sir. Okay, sir. I will send this.
I'll type my mail ID in the chat box.